Have you ever played a board game where every move depends on the roll of a dice? You don't always know where you'll end up next, but each move follows a pattern guided by chance. Wait and hold your answer there, because it has everything to do with Markov chains. Good day! I'm Rainier Joseph Talite from Group 5, along with my co-presenters Jehel Ferwello, Zaira Lansigan, and Frances Joy Lim from BSCS 3BM. In this video, we'll be walking you through the fascinating world of Markov chain movement tracking state transitions. So, buckle up as we explore how state transitions work and why they matter in the world of modeling and simulation. Zaira, take the floor please.
Hi, I'm Zaira Lansigan and I'm here to explain to you all about the Markov chain. Let's begin with the basics. A Markov chain is a mathematical model that describes a sequence of events where the next event or state depends only on the current state. This is what we mean by it being a memoryless. For example, if you're in a state A now, the next state you move depends only on that, not on how you got to state A. We use Markov chains in simulations because many real-life systems behave randomly, like predicting the weather, tracking board game positions, or modeling customer behavior. These systems change over time, and Markov chains help us understand those changes in a structured way. The main goal of our activity is to simulate this type of system using a die, which adds randomness. We'll track the transitions over time and try to estimate the steady-state probability, which tells us how often we might expect to be in each state in the long run. In our activity, we're working with a simple system made up of three states, A, B, and C. Think of this like possible conditions or positions the system can be in. We use a six-sided die to decide where to move next from any current state. The roll of the die tells us which state to go to. So instead of a fixed rule, like A always goes to B, the next state is chosen at random based on the die roll. This randomness is key. It makes the system probabilistic, which means transitions happen based on chances, not certainty. For example, you might stay in the same state or you might move to another, depending on the roll. Also, because we're simulating a memoryless system, the next move depends only on where you are right now, not on how you got there. That's an important feature of Markov chains. Here's how we actually simulate movement from state to state. We roll a regular six-sided die, and no matter which state we're currently in, A, B, or C, we always follow the same rules. If the die shows 1 or 2, we move to state A. If it shows 3 or 4, we move to state B. If it shows 5 or 6, we move to state C. This means every state transition is based on a 1 out of 3 chance, or about 33%. There's no bias. Each state has an equal chance of being the next one. This setup makes it easy to simulate the process. We just start in any state, roll the die, move to the next state based on the result, and repeat the process for 50 steps. By keeping track of how often we visit each state, we can start to see patterns and estimate the system's long-term behavior, or steady-state probabilities. And that's all for the introduction of the Markov chains in our activity.
Welcome to this walkthrough of our Markov chain simulation. I'm Rainier Joseph Talite, and I'll be guiding you through both the conceptual flowchart and its implementation using pseudocode. Let's begin with the flowchart. This diagram represents the entire simulation process from start to finish. The simulation begins by setting the current state to A. All state counters are initialized to 0, as well as an iteration counter to track our progress. The simulation runs for 50 iterations. During each cycle, a die is rolled to generate a number between 1 and 6. Based on the result and the current state, the simulation determines the next state, updates the appropriate counter, and moves to the next iteration. Each state follows its own set of transition rules. When the system is in state A, rolls from 1 to 3 keep it in A, 4 and 5 move it to B, and 6 moves it to C. In state B, rolls of 1 or 2 transition back to A, 3 or 4 keep it in B, and 5 or 6 shift it to C. For state C, a roll of 1 sends it to A, 2 or 3 lead to B, and any number from 4 to 6 keeps it in C. After completing all iterations, the simulation calculates the probability of being in each state by dividing each state's count by the total number of iterations. Now, let's see how this process is represented in pseudocode. The code begins by setting the initial state to A and preparing counters for each of the 3 states, all starting at 0. A loop runs 50 times. In each cycle, a random number between 1 and 6 is generated to simulate a die roll. If the current state is A, the code checks the roll and applies the same rules from the flowchart to determine the next state. Similar blocks of conditional logic handle transitions when the current state is B or C. After updating the state, the code increments the corresponding counter, and once all iterations are complete, it prints the final counts, which represent how often the system landed in each state. The flowchart and pseudocode represents the same system from 2 perspectives. One visual, the other logical. Now, I'll pass it on to Frances, who will present our simulation results.
Good day everyone, I am Frances Joy Lim, and today I will be presenting our simulation results analysis. We conducted 3 separate simulations with 50 steps each, starting from different initial states. Simulation 1 began in state A, simulation 2 in state B, and simulation 3 in state C. These simulations were performed using virtual dice rolls on a website called Stopwatch Roll a Dice to determine state transitions according to our predefined rules. So now for our state transition mechanism, our system moves between 3 possible states, A, B, and C, with transitions governed by both the current state and the outcome of a dice roll. For example, when in state A, rolling a 1 or 2 keeps the system in state A. Rolling a 3 or 4 transitions to state B, while rolling a 5 or 6 moves to state C. Similar rules apply for the other states, creating a stochastic process with interesting behavior patterns. Now let's look on our state visit count table. Looking at our occurrence table, we can see the distribution of visits across the 3 states in each simulation. Interestingly, state A was visited exactly 19 times in all 3 simulations, representing 38% of all visits regardless of the starting state. However, we observed significant variations in states B and C. In simulation 1, starting from state A, we see a relatively balanced distribution. Simulation 2 starting from state B shows a strong preference for state B with 22 visits, and simulation 3 starting from state C shows a higher occurrences of states A and C with fewer visits to state B. Now, as we can see here in our graphical comparison of state visits, this bar chart provides a visual representation of our state visit distribution. The orange bar represents state A's visits, blue represents the state B, and green represents state C. The consistent height of the orange bars across all simulation confirms our observation about the state A stability. However, notice how the blue bars for state B are much taller in simulation 2, while the green bars for state C are more prominent in simulation 3. This visual comparison makes it easier to identify patterns and differences between simulations. So for our key observations, to summarize our key findings, First, the remarkable consistency in state A visits suggests some form of equilibrium or attractor in our system. Second is that, despite this consistency in state A, the starting state appears to influence the long-term behavior of the system, particularly for states B and C. This suggests a form of memory in the system where the initial condition continues to impact the system even after many transitions. These patterns could indicate properties of the underlying Markov chain that governs our system's behavior. Now, I will hand over to my colleague who will discuss the theoretical implications of these results. Let's please welcome Ms. Jahel Ferwello.
Hello everyone, I am Jahel Ferwello. I'll discuss our estimated steady-state probabilities from the Markov chain simulations and how they compare to theoretical values. We ran 3 separate simulations starting from different states to observe conversion patterns. To estimate the steady-state probabilities, we use a straightforward approach dividing the visit count for each state by the total number of rolled dice. This gives us the proportion of time spent in each state. So the table here is our key findings from the 3 simulations. In simulation 1, starting from state A, we observe probabilities of 0.38 for state A, 0.34 for state B, and 0.28 for state C. In simulation 2, starting from state B, we saw 0.38 for A, 0.44 for B, and 0.18 for C. And lastly, in simulation 3, starting from state C, the results were 0.38 for A, 0.24 for B, and 0.38 for C. When averaged across all simulations, we found consistent probabilities of approximately 0.38 for state A, 0.34 for state B, and 0.28 for state C. And now for the crucial part, comparing simulation results with theoretical predictions. From our 3 simulations with different starting points, we found remarkably consistent average probabilities. State A converged to 0.38 across all simulations, while states B and C showed more variation between individual runs but consistent averages. The theoretical steady-state distribution calculated from the transition matrix aligns closely with our simulated values. These conversions demonstrate a fundamental property of ergodic Markov chains regardless of starting state. They eventually approach the same equilibrium distribution. The slight variation between the theoretical simulated values can be attributed to our finite sample size of 50 rolled dice. With longer simulations, we'd expect even closer conversions to theoretical values. To conclude this, our simulations effectively demonstrate how Markov processes approach steady-state probabilities over time. What this means that after enough steps, the system settles into a pattern where the chance of being in any states become predictable and stable. Just like how a ball eventually stops bouncing and comes to rest, our Markov chain finds its balance point. The consistency of state A probabilities across all simulations highlight the ergodic property of this Markov chain. Ergodic means that no matter where we start, we'll end up with the same long-term behavior. Notice how state A always ended up with a 0.38 probabilities regardless of starting position. This isn't coincidence but a fundamental property of these systems. Multiple simulations with different starting points were crucial for verifying our results. By starting in state A, B, and C separately, we prove that initial conditions don't matter in the long run. This is like showing that whether you enter a shopping mall through the front, back, or side entrance, you'll still spend roughly the same amount of time in each store if you walk around long enough. And lastly, this simple model illustrates powerful concepts that apply to many real-world systems. Weather forecasting uses similar ideas to predict temperature patterns. Online recommendation use Markov model to guess what you might like to watch next. Even the market analysis sometimes uses these principles to understand price movements.
And that brings us to the end of our presentation on Markov chain movement. On behalf of Group 5, thank you for being part of this learning experience.